Hi class, welcome back. Today we're gonna discuss the fundamental theorem of calculus. So we're gonna be able to connect a lot of the pieces that we have discussed in the previous sections. So some of the objectives for these sections are to evaluate a definite integral using the fundamental theorem of calculus, understand the use of the mean value theorem for integrals, find the average value of a function over a closed interval, understand and use the second fundamental theorem of calculus, understand the use of net change theorem. So, the fundamental theorem of calculus. You have now been introduced to two major branches of calculus, differential calculus and integral calculus. At this point, these two problems might seem unrelated, but there is very close connection. The connection was discovered independently by Isaac Newton and Gottfried Leibniz and is stated as the fundamental theorem of calculus. Informally, the theorem states that differentiation and definite integration are inverse operations. In the same sense, the division and multiplication are inverse operations. To see how Newton and Leibniz might have anticipated this relationship, consider the approximation shown in the figure to the right. So we see here the derivative, right? The derivative, the tangent line of a function, and here we can also see the derivative of this line right here, right? This is a secant line, this is a tangent line. If you notice here, we are able to approximate the differentiation by using the secant line. We're able to actually find the slope of that point by using the tangent line. And here we're able to approximate the area of the rectangle, but here we're able to actually find the area of the rectangle. And either way, in either cases, do you notice that we end up using the differentials of y and x, differentials of y and x, the differentials of y and x, differential of y and x. So differentiation and definite integration have an inverse relationship. The slope of the tangent line was defined using the quotient of delta y over delta x, also known as the slope of the secant line. Similarly, the area of the region under the curve was defined using the product of delta y times delta x, the area of the rectangle. So at least in the primitive approximation stage, the operations of differentiation and definite integration appear to have an inverse relationship in the same sense that division and multiplication are inverse operations. The fundamental theorem of calculus states that the limit process use the derivative and definite integral to preserve the inverse relationship. Theorem 4.9, the fundamental theorem of calculus. If a function f is continuous on a closed interval from a to b, and f is the antiderivative of little f on the interval from a to b, then the definite integral from the endpoints a to b of f of x dx is equal to the antiderivative of little f at b minus the antiderivative of little f at a. So what this is saying, if we're able to take the antiderivative of f first, then we can evaluate at b minus a, independent of each other. And so we no longer have to rely on the limit definition that we discussed in the previous section. The following guidelines can help us understand the use of the fundamental theorem of calculus. Guidelines for using fundamental theorem of calculus. Provided you can find an antiderivative of little f, you now have a way to evaluate a definite integral without having to use the limit of a sum. When applying the fundamental theorem of calculus, the notation shown below is very convenient. So we often use this notation. The definite integral from a to b of f of x dx is the antiderivative of little f, which is f of x, from a to b. So we use this. So what we're going to do first is we're going to find the antiderivative of f, which is this. Then we write sort of this line right here and say to the reader, we're going to evaluate this from A to B, and we go first with B, right? We first plug in B into the function, into the entire function, replace x with B, minus, then we try that again, but now with A, with the lower limit. And this gives us the definite integral. So for instance, if I give you and I ask you to evaluate the antiderivative, the definite integral of from 1 to 3 of x cubed dx, then you can write first the antiderivative of x cubed, which is x to the 4 over 4, using the power rule. Then we're going to write a line here telling the reader that we're going to evaluate this from 1 to 3. So first we're going to replace x with 3, such as 3 to the 4 over 4, followed by a minus, and then replace x with a 1 to the 4 over 4. Then once we have set it up, then we can go ahead and simplify this as much as we can. The 3 to the 4 is 81, followed by the division of 4, minus 1 to the 4 is 1. So 81 over 4 minus 1 over 4, they both have common denominators, so we can proceed to subtract the two fractions. 81 minus 1 is 80 over 4, which is equivalent to 20. So it is important for us to discuss why there's no c anymore. We done the indefinite integrals before, and we were adamant for us to always contain that c, right, that constant c, because it was needed for us to be able to write a general solution or a general equation of that indefinite integral. But let's see, if we proceed with the c, we will see that c will actually cancel algebraically. So let's proceed again. Use the same argument. So we'll use find the antiderivative of f of x, which is f of x plus c, right? So let's say we are carrying that c now, right? Let's say. So we plug in b and a. So the first one will be f of b plus c minus, now the case when you plug in a, f of a plus c. Now if you notice, this will give us negative f of b, so negative f of a, so negative b minus f of a will be those two. But then you have plus c minus c. Well, they're gonna cancel each other out, so therefore there's no c. So even that argument will follow here that you should have a c, but at the end of the day we all know that c will cancel each other out. So please note that it is very common for us to do it this way. So we'll do it this way. This is going to be the structure and the technique that we will follow. So there's no need for us to worry about c when we're dealing with definite integrals. I hope that kind of makes sense. Alright, so we're going to try a few examples now using a combination of rules that we have discussed with the indefinite integral, right? So what the last rule is suggesting is that every rule that we discuss in the first section regarding indefinite integrals, you know, the ones such as the power rule, the sine and cosine, the tangent, the secant, all the addition, subtraction, the constant, all those rules are now applicable to the definite integral, and there will be sort of follow-up in here. So let's try the first example. Let's find the definite integral from 1 to 2 of the function x squared minus 3 dx. So first we'll begin by applying the antiderivative of each of the terms. So the antiderivative of x squared is x cubed over 3, right? What do? We add 1 to the power first and then divide by the new power. Do you guys see that I didn't do this? I didn't divide by the power and then added 1. No. The rule says first add 1 to the power and then divide by a new power. That's power rule. And we had to use power rule because we have a power function. Here we have a constant, and so when we have a constant, the antiderivative of that will be adding the variable. In this case, the variable will be in terms of x. So there you go. So minus 3x. Then we draw this line telling the reader that we're going to evaluate at 1 and 2. So first begin by plugging in your 2. So I did that, plug in 2, put a bracket to tell the reader that this is a specific number, followed by the minus, right? According to our formula, we're going to follow a minus, right? Followed by the minus, and then now plug in 1, plug in 1, plug in 1. And we did that. Notice I put a bracket. It's very important for us to put a bracket because this negative needs to be distributed to both terms. Failing to do that will fail for us to get the right answer, right? Because the computation will be wrong. Then at this point you're done doing the algebra, the calculus part. After this is just pure algebra. We're gonna have to simplify. 2 to the third is 8 all over 3 minus 6 minus 1/3, and then distribute this plus 3. Combine like terms, so 8 over 3 minus 1 over 3 is 7 over 3. Minus 6 plus 3 is negative 3. Combine fractions by having common denominator, so multiply this one by 3 over 3. And now we have 7 minus 9 over 3. So that gives us negative 2 over 3. So the definite integral, this is equivalent to an actual value now. It's an actual value. So if you guys noted that for the indefinite integral in the first section, we actually came up with an algebraic expression, right? We found an expression. We found the function, the regional function, right? In this case, what we actually finding is an actual real number. So let's try the next one. Find the definite integral from 1 to 4 of 3 times the square root of x dx. The first thing to do here is to rewrite the square root in the form of a power. So this will give us 3 times x to the 1/2. Then now let's find the antiderivative of this. Well, the constant is being multiplied to the function, so by the constant function rule, the constant follows. The antiderivative of this will follow power rule because we have a power form. So will be add a 1 divided by a new power, right? So 1/2 plus 1 is 3/2 divided by 3/2. Then we're going to evaluate this from 1 to 4. And then, but before we do that, we're going to simplify this expression. We can see that 3 is going to be multiplied to the reciprocal of the denominator, right? What happens when you divide it by a fraction? You change it to by multiplying by reciprocal. We see that 3's will simplify and cancel each other out. So you're pretty much left with 2 times x to the 3/2 from 1 to 4. So I rewrote it in that form. And then I'm now going to evaluate it. So I'm going to plug in 4 for the first one. So plug in 4, replace x with 4, minus, now replace x with 1. The square root of 4 is 2, to the third power is 8. So that gives us 8 times 2, gives us 16. 1, the square root of 1 is 1, to the power of 3 is 1, times 2 is going to be 2. So 16 minus 2. 16 minus 2 is 14, and we're done. So let's try the next one. The definite integral from 0 to pi over 4 of the secant square of x dx. First begin by finding the antiderivative of secant square x, which is tangent x. We're going to evaluate that from 0 to pi over 4. This is going to equal to, first replace x with pi over 4. We did, followed by a minus. Now replace x with 0. That gives us tangent of 0. Equals to, the tangent of pi over 4 is 1. The tangent of 0 is 0. So it gives us 1 minus 0 is 1. So there you go. The indefinite integral of this definite integral is 1. All right. Here's another problem we want to discuss. So here we have a, I'm going to try practice number 2. if we draw this function, this means that this is going from 0 to 2. Now this function happens to be a function that is being shifted into so this function is being shifted, right? So if we notice, we have a function that is 2x. So we draw this line. This line will be the slope is 2, but the y-intercept is -1. So this function will start here, and then we'll have a slope of 2, so it'll be 1, 2, 1, 2. So it will look like over here, 1, 2, like this. All right, so we'll pass through this 1/2, right? So this 1/2. This is 1 right there. But because there's an absolute value, the absolute value will make this positive. So what's going to happen is that instead of going down here, it's actually going to bounce back. So it's going to bounce back. So it's actually going to be up here. So what we're looking for in this is not the bottom part. We're not looking for the bottom part. We're actually looking for the area under this graph. So it'll be this right here, or sorry, the integral of this, which will be right here. All right, so that's what we're looking for, right? We can do it geometrically by just finding the area of this triangle and add it to this area of this triangle, or we can do it in a different way. So let me try that over here. So let's do that. But for this, we're going to have to do a separation of function. So if we think about this, 2x minus 1 is going to be always positive. So whenever x is less than 1, then we notice that was negative, right? That was negative. Well, we notice that this was a negative value, but we can make it a positive by putting a negative in front of it. So it'll be like negative like that. After you pass, and that means the 1/2 here instead of 1. After you pass the 1/2, then the value of this was greater than 0. So the value of the function was actually greater than 0. So 2x minus 1. So I remind you that we have to do this is because this needs to stay positive, right? It's an absolute value. So what we're going to do here is we're going to separate this into two functions. So we go from 0 to 1/2, right? We're going to separate it into those two pieces of functions. And we're going to say, if for this function, we're going to have the negative value multiplied by negative dx. And then we're going to add it from 1/2 to 2 for the other function. Do you guys see that? This now is positive, and then this is positive, but we needed to separate them because the function was only negative between those two values. So, all right, I hope that kind of makes sense. Now we can kind of do these two on their own. So we're going to erase this part now. And now we're going to take the antiderivative of both of them. So what we're going to do here is, and remember that we are allowed to separate them because some of the properties that we discussed before. So we're going to separate this into two integrals, and now we're going to do the integral of both of them. So the first one will be negative from 0. So it'll be the integral of 2x will be 2x squared over 2 and then minus 1 times x, right? We have to add the x. And we're going to evaluate this from 1/2, sorry, from 0 to 1/2. Plus, the integral of this will be pretty much almost the same thing, 2x squared over 2 minus 1 times x. And then we're going to evaluate this from 1/2 to 0. Okay, so now we're gonna we're gonna simplify a few things such as those two, and then now we're gonna evaluate. So we're gonna have negative for 1/2 squared minus 1 times x, which is just 1/2. And then minus, but then we gotta be careful because there's a minus in front of this whole thing, right? So we're gonna be minus minus. So it'll be now 0 squared minus 0. And that was just the first integral. Now we're gonna do the second one. So it'll be plus, now we're gonna plug in now we're going to plug in the 1/2. So it'll be plugging in 1/2 in here will be 1/2 squared minus 1/2. And then followed by, oopsie, I jumped here. I meant first starting with my 2. Sorry about that. So it'll be 2 squared minus 2 minus the 1/2 squared minus 1/2. And there you go. So we can see that this all depends on 0. They're all 0, so that's just going to be 0. So we don't have to worry about that. Now, if you notice here is that this will be distributed to those two, making the first one be negative, which is just going to be the same thing as we would do over here. So that means that this happens to be the same as this, and this will turn into a positive, just like this will turn into a positive. So we end up getting 2 of those. I hope you guys are able to see that. So I'm just going to rewrite those as 2 times negative 1/4, right? Because 1 over 2 squared is 1/4, followed by a plus of 1/2, and then followed by 4 squared minus 2 is 4 minus 2 is just 2. All right, so that will simplify a little bit. This right here is 2 over 4, so that will be 2 over 4 minus 1 over 4 will be 1/4, so it'll be 2 times 1/4 plus 2 will give us, am I missing a negative somewhere in here? I'm going to look at my notes here real quick. Sorry about that. -5/5. Actually, this is supposed to be positive. It's supposed to be a positive 5/5. So that's a typo right here. Sorry about that. So that should be 5/5. There you go. And then, all right, so that looks good. And so that'll give us 1/2 plus 2, gives us 5/5. There you go. All right, so there you go. But the point of this one was the separation of the two absolute values. All right, and I'll let you guys try number 3 on your own, or you can ask that on a lecture. So the next topic we want to discuss is the mean value theorem. The mean value theorem gives us an opportunity for us to discuss the condition of a mean value, right? With the connection with the integral. So I'll briefly describe that here. So let's say you're given this function, right? The mean value of this function, because the function changes over time, right? Over x, the value of x changes. It gets lower, and then increases, and then it starts lowering again. So the value of the function is different for every x between a and b. So what we're saying here is that we are able to find the average value of the function, meaning the average between these values right here, right? Because the value of the function goes up and down, we can find an average value of the function. And how do we do that? It's actually pretty clever. So it actually comes using the integral. If you notice, if we have this region and I ask you to find the area under the curve, notice that if we can find out where the average value of this function is, it would be whenever this piece complements the other piece, meaning that the same value happens underneath as it happens over it, right? So what we're saying here is if you can find this piece and put it there, then what you're gonna get is an average value of the function right here. This will be the average value of the function. So in other words, there is some c, if you notice, there's some c where eventually the function will equal the average value of the function, and that will happen at c. Now obviously the function needs to be continuous, right, and differentiable. So but if we notice, we can actually do that over here. If you notice here, if we can find that value by doing this clever approach. What is the area of this? If we can find the area, then we can find this value, right? So if we know that b minus a gives you this, and if you multiply this by the height f of c, then that will give us this. We know that f of c is the height of this rectangle. So we know that this area right here is the area of the rectangle. Well, but we also know that that's the same thing as the area under the curve, right? The area under the curve. We said because this part over here, this area was put over here to complement it. So these two are the same, right? These two are the same. Well, if our goal is to find the average value of the function, all we have to do is basically solve for f of c, meaning all we gotta do is divide both sides by b minus a, or 1 over b minus a, and that's going to be our formula. So let me just go over this real quick. The mean value theorem for integrals, you saw that the area of the region under the curve is greater than the area of an inscribed rectangle and less than the area of the circumscribed rectangle. The mean value theorem for integrals states that somewhere between the inscribed and the circumscribed rectangles there is a rectangle whose area is precisely equal to the area of the region under the curve, as shown in the figure on the side. So theorem 4.10 generalizes this result. It states that the mean value theorem for integrals, if f is continuous on a closed interval from a to b, then there exists a number c in the closed interval from a to b such that the definite integral from a to b of f of x dx is equal to f of c times b minus a. Well, the mean value theorem states that, but we can actually extend this further. We can say that the average value of a function, the average value of this function, f of x, can be found by doing the following. The value of f of c given in the mean value theorem for integrals is called the average value of f, the average value of f on the integral from a to b. So by definition of the average value of a function on an interval, f is integrable on a closed interval from a to b, then the average value of that same function on that interval is going to be 1 over b minus a from definite integral of a to b f of x dx. So please note that what we're doing here is finding the average value of f of x. We're finding the average value of f of x. Alright, so here this extends this procedures further, so we can just you guys can go over that one on your own and let me know if you have any questions. So that just sort of gives you a little more abstract of this theorem. Alright, so let's try example 4. Let's find the average value of f of x, right? So f of x is the function and we're going to find the average value of f of x. And basically all we're going to do is take f of x and do the definite integral from the endpoints, multiply this by 1 over b minus a. So you guys know how to do this. All we're doing is just adding this little condition here. So basically we're doing the same thing we did before. Definite integral from 1 to 4, 3x squared minus 2x multiplied by 1 over 4 minus 1. This is your a and this is your b. So we'll start by doing the antiderivative of this, which is 3x cubed over 3 minus 2x squared over 2. Multiply this by 1/3, right, with the 1/3 from there, and then apply this from 4 to 1. So we began by applying the 4 first, and that will give us 4 to the third minus 4 squared, everything multiplied by 1/3, minus 1/3 times 1 to the third minus 1 to the second. Notice that made it easier because I simplified it before. I highly encourage you guys to do that. Next, we're going to simplify this. This is going to be 4 to the third. That's 64 minus 16. That's 48 times 1/3. And then this is going to be 1/3 minus 1. That's going to be 0. So that's just going to be 0. 48 times 1/3 is 16. So the average value of this function between 1 and 4 is 16. So here's your f of x, right? Here's your f of x. Fascinating that we can just find the average value of this function. And this will be 16. Alright, so we're going to move on to the second fundamental theorem of calculus. So we already discussed the first fundamental theorem of calculus, the fact that we can find the definite integral using the concept of the antiderivative. But in that case, it happened to be that this was a constant and that was a constant, right? And then here was our function of x. Well, the difference between that and the second fundamental theorem of calculus is that this one, instead of giving us an actual number, an actual real number, instead of getting a real value, we are actually gonna get a function back. How? Well, the function will be in terms of x, which instead of having a constant, we're gonna have a variable. So we won't be plugging the last number that we're gonna plug in won't be a constant. We actually be a variable. So this one will be matching this one. So that means that we're going to be differentiating in respect to a different variable, right? So do not get caught up too much in this. This just needs to be a different variable than this. That's all we're saying. So this could be in terms of y, this can be in terms of u, this can be any variable you want. This is just a dummy variable. So that this is just saying find the antiderivative first, and then apply the x and the a. So let me show you what I mean. Find the definite integral of a function evaluated by the function this. Now we know that we have to use the second fundamental theorem of calculus because we have a variable instead of a constant. So it's sort of giving it away, right? We don't never have to guess which one we have to use. It's the same concept. It's just the fact that we're given a variable instead of a constant. So let's do that. So we're going to find f of x. We're going to find this definite integral. We're going to first start by finding the antiderivative of cosine, which happens to be sine. Notice that these two have to be this variable needs to be different than this one. So the antiderivative of cosine of t is sine of t. We're going to evaluate again from 0 to x. So that means first we plug in an x, and then second we plug in a 0. And that's it. This is it. Now you can simplify by knowing that sine of 0 is 0. So we end up getting sine of x. And that's it, right? So f of x is sine of x. So we no longer we get a real number, but we're getting an actual function. And notice that there's no plus c here, right? There's no plus c. And you guys know because that's a definite integral. So, but now they're asking us to evaluate this function at x equals 0, at pi over 6, at pi over 4, and so on and so on. So plug in 0, sine of 0 is 0, plug in pi over 6, gives you 1/2. Add pi over 4, you get square root of 2 over 2. Add pi over 3, you get the square root of 3 over 2. Add pi over 2, you get 1. And so on, right? So once you find this one, it's very easy for us to find all the rest of the values. We don't. The good thing about this is that we don't have to do the integral over and over again for every single value of x, right? We can just use the second fundamental theorem of calculus. All right. So, and the one interpretation we can use here is we can think about that this. We remember that we can always refer a definite integral to be the accumulated area under the curve, right? We always say that, oh, this could be used to find the area under the curve. Well, think about it. Maybe this could be the same thing, right? This could be the accumulated area under the curve from 0 to some non-specified x value. So you can think of the function f of x as accumulating the area under the f of t, cosine of t, from t equals 0 to some t equals x. So for x equals 0, there is 0. For f of 0, you get 0, right? For x equals pi over 2, you get 1, which gives you the accumulated area under the cosine curve on the entire interval from 0 to pi over 2. This interpretation of the integral as an accumulation function is used often in application of integration. In example 5, note that the derivative f is the original integrand with only one variable change. That is, if you find the derivative of this, that means you're finding the derivative of sine of x, which means you're finding the derivative of the antiderivative of this, which is cosine of x. So we can sort of also use the previous result to help us that. So this will give us now the chance to generalize the following theorem called the second fundamental theorem of calculus. So if f is continuous on an open interval I containing a, then for every x in the interval, we will have the derivative in respect to x from a to x f of t dt is going to be equal f of x. So what we're saying here is sort of the idea of this, right? If you take the derivative of the definite integral, then you're going to end up getting the value inside the integral, the integrand, in terms of that variable. And that's what we're getting, right? So sort of they cancel each other out, but the end result will be f, the function, in terms of that variable. All right, so let's use a few, let's practice this concept. Let's evaluate the derivative respect to x of the definite integral from 0 to x of the square root of t squared plus 1 dt. If we know this is continuous from 0 to x, then that means we can use the second fundamental theorem of calculus and suggest that these two will cancel each other out, and all we have then result will be the square root of the function in terms of that variable. So it'll be instead of t squared, will be x squared, the square root of x squared plus 1. And that's it. So in the next one, it's sort of also consistent, right? We're gonna have we're gonna apply find the derivative of this, but the derivative of this will be so sort of like cancel each other out, and then this is gonna go here. But then we're gonna also have to multiply it to the derivative of our function. So notice that if you apply the antiderivative of this, you will get to this, and by using cancellation and be able to simplify some of the steps there. Okay, so let's try another example here, the net change theorem. The net change theorem suggests that if f is continuous on the closed interval from a to b, and f is the antiderivative of f from a to b, then we're going to have this definite integral. So we're going to call, so we can rewrite this as saying, well, if we write this f of x instead of using little f, we can write it as the antiderivative of f of x. Then basically we're saying is like you're undoing the derivative with the integral, and that's how we get this difference, right? Well, this is sort of a good connection for the net change, because often for the net change, they're going to give us the rate of change. They're going to give us this, the rate of change. Remember, rate of change means derivative. So they're going to give us the derivative, and they want us to find the net change of that rate change. And so that means we're going to have to find the original function and then subtract the difference between those two. Net change means the total difference, right? Total difference, net change. So the definition of this will be that definite integral of the rate of change of a quantity f prime of x gives the total change or net change in the quantity on the interval by applying this definite integral. So let me show you an example of that. Using the net change theorem, a chemical flows in a storage tank at a rate. So they're giving us the rate. Liters per minute, that's another sign of rate, between 0 and 60. Find the amount of chemical that flows into the tank during the first 20 minutes. They're giving you a rate, so this is a derivative. Now the amount is the total value, right? So that's amount of value, so that's f of t. Now they want us to find the total amount between 0 and 20, or they could have said from 10 to 20, right? They can say in the second in the amount of flow between the 10th minute and the 20th minute. It won't matter, right? Because you're gonna have an initial value and in a lower bound and upper bound. So in this case, right, we wrote down our value, our rate of change, and we're gonna go from 0 to 20, right? 0 to 20 minutes. and notice that this is minutes and that's minutes, so we don't have to make any conversion. If we had minutes and seconds, then we needed to do some conversion. So we're going to follow the formula instead and take the definite integral of this rate of change from 0 to 20. So the antiderivative of f prime is going to be the original function. So we're going to pretty much do the amount in 20 minutes minus the amount in the 0 minute. And so we're going to do that by applying that to the original function, to this given function. So the antiderivative of 180 plus 3t will be 180t plus 3t squared over 2. Then plug in 20 into the equation, and then plug in 0 for the second part of the equation, right? So plug in 20, replace t with 20, and replace t with 0. Compute all that, simplify it using algebra, and that will give us 3600 plus 600, which gives us 4200. What this is saying is that the amount that flows into the tank during the first 20 minutes is going to be 4200 liters. The amount of flow in the first 20 minutes, it will be 4200. Now this could be changed again very easily if I wanted to find how much amount of flow happened between the 10th minute and the 20th minute, right? So that would have been 10 and that would be 20, 10 and 20. And the problem would have been just about the same thing. All right, so another application of the net change is when we deal with velocity and displacement. So to examine to illustrate this, the net change theorem is for us to examine the velocity of a particle moving along a straight line, where s of t is the position at time t. Then its velocity, v of t, is the derivative of the position function. And thus, we know the definite integral of velocity is going to be the position b minus position at a. Well, the definite integral represents the net change in position, the net change of position. So, but if you guys notice, that's where you were, right? So how much is difference between when you were at this time versus in this time, also known as displacement. Now there's something interesting about this, and that is that a lot of times we actually want to calculate the total distance traveled, right? So displacement doesn't actually reflect the actual total distance traveled by the particle. You actually must be considered where the velocity was negative, meaning it was moving in the opposite direction, and then the interval where v of t was actually positive as well, when it was moving in the positive direction. So when the velocity is moving in a negative direction, the particle, when the velocity is negative, the particle is moving to the left, and then when the velocity is positive, the particle moves to the right. So to calculate the distance traveled, we have to integrate the absolute value of both velocities. So let me show you what we have here. So here we have positive velocity, but then we have negative velocity, and then we have positive velocity. So if you notice, there's some sort of cancellation in here, and so in order for us to fix that, what we need to do is we're going to make sure that everything is positive. Everything is positive, because we want to know how much we travel, right? How much total distance we travel, not the difference between positions. So difference between positions doesn't take into account that you actually walked 10 miles, but then you walk 5 miles one way and 5 miles back the other way. For displacement, there was no change there because you're in the same position. For total distance travel knows that you travel 5 miles in that direction, and then 5 miles, an additional 5 miles to move in this direction. So how would you do that? Well, whatever value of velocity is positive will stay positive. Whatever is negative, you're going to make it a positive. If this is negative, put a negative in front of it. That will make it a positive. And then this is positive, so that's positive. So in other words, what we're going to have is we're going to make sure that everything that you add up is positive. So here's an example of this. So we have solving a particle problem, the velocity in feet per second of a particle moving along a line. So this is the velocity where t is in time in seconds. What is the displacement of the particle at the time interval between 1 and 5? Well, that one's going to be very straightforward, right? That's just going to be the definite integral, and that's what we did, right? We did the antiderivative of this whole thing, which is right there, evaluate from 5 to 1, plug in the 5 there, plug in the 1 there, and then do the hard algebra there, and then just simplify it, and that gives us 32/2. So that one's not so bad. For the total distance travel, we have to be a little more careful. We're going to make sure that everything that we are calculating is positive. Now in this case, we know how the function looks like, so we know there is some negative part over here. Velocity was negative between 4 and 5. So what we're going to do here is we're going to separate this into two definite integrals. One between 1 and 4, because we know it's positive, so there's no need to be changed. There's no change needed. Another one from 4 to 5. This is where the velocity was negative, so we're going to have to multiply by negative to make this positive. Remember, negative times negative becomes positive. So now this is positive. So you have a positive velocity plus a positive velocity. So you're going to have to do two different integrals. One from this, so that gives us this, evaluate from 1 to 4, and then do the integral for this one from 4 to 5, right? Don't forget that this minus was carried outside, so that's your minus there. Now it does require some organization, and be careful with your data. So plug in the 4, and I did, and then minus, plug in your 1, which I did. For this one, follows by a minus, a big bracket. Now plug in for the 5, that's that one, minus, plug in for the 4, and that's that one. Now there's a bracket there, so that one's going to be carried to this and that. But if you notice, negative times negative becomes positive. So this one's going to be the same thing as that one. So pretty much whatever I calculated there is going to be added the same thing here. So it'll be 8/3, right? I did this and I found this is 8/3. So I'm going to multiply that by 2. When I did this one, that gave me negative 103/12, and there's a minus in front of it, so that's going to simplify. And then here this became minus 25/12. I calculated this whole thing, and that gave me 71/6. Over 6. That one should be a 6. All right, and so there you go. So we found that that was the total distance travel versus the actual displacement of the particle. Okay, so I hope you guys find this helpful. Please let me know if you have any questions, and I'll see you guys next time.